Good morning, everyone. I would like to thank organizers of Nickel Cobalt Symposium for the opportunity to talk about the progress in the thermodynamic database for nickel and cobalt pyrometallurgical applications. First, let's have a look on recent trends and events that I believe had big impact on the pyrometallurgical refining of nickel and cobalt. Of course, the governments of Canada, Australia, and EU are very serious about decarbonizing targets, which may or may not help to slow down the temperature rise in the next decades. This is yet to be seen. What we already see is the significant increase in the energy costs, which paradoxically contributed to the shutdown of the low CO2 nickel production from sulfide ores in Australia. Energy cost is one of the factors, but export protection by Indonesia, followed by the Chinese government subsidized buildup of nickel refining capacity, created the distorted market. Most of production in Indonesia is ferronickel, and once they flooded the market, places like New Caledonia could not compete as well. The green irony is that high CO2 nickel pig iron produced using coal-fired power plants must be further refined into battery-grade materials destined for EV transition. This undermines the efforts to decarbonize by other countries and hurts the image of EVs. This contributes to slowing down of EV boom and moving away from nickel as a battery material. This is bad news for companies and governments who invested a lot in battery recycling through shredding, anticipating large quantities of black mass in future. The bankruptcy of Li-Cycle in the US is the most telling example. The company stated the escalating costs were specifically related to the installation and labor costs for mechanical equipment, piping, structural steel, electrical and instrumentation for the measurement and process control devices. In other words, shredding turned out to be expensive. Furthermore, battery shredding has always carried a risk of massive fire, requiring deep discharging and substances creating inert atmosphere, all contributing to the cost. The explosion in Missouri battery plant demonstrated how hard it is to mitigate those risks. I tried to find out the cause of the fire, namely, what was it in the storage facility or in the battery shredding? The best quote I found is, "The battery started when a machine was processing cathode foil." Now let's look at other developments that may influence the pyrometallurgy of nickel cobalt in the next 5 years. In response to market monopolization and supply restrictions, countries create a list of critical minerals. This is really a misnomer. We must call them critical elements. For instance, Australia produces gold antimony concentrate, which is a mineral, but then ships it all to China for refining. Now, with the Chinese restrictions on refined antimony, no other countries can get access to Australian mineral of antimony. The rare earth story is similar. It is the refining capacity which makes the production particularly concentrated. In response to the rise of high CO2 nickel, EU is considering battery regulations and carbon footprint performance classes. Europe's regulations are slow to implement, but in my opinion inevitable, because bureaucracies would love to regulate more given the opportunity and public support. Thus, battery nickel produced from sulfurization of nickel alloys from laterites may find customers only in China, who themselves are shifting towards lithium iron phosphate chemistry. Thus, places with sulfide ores may become more competitive and support EU's battery production using high nickel cathode materials, which still have the energy density advantage. Finally, a note about battery recycling. We will likely have less volume to recycle, with less cobalt in them, but recycling is still good if done economically and safely. Of course, I have a bias here, but pyrometallurgical production of unprocessed modules in the high temperature furnace makes quite a lot of sense to me, as opposed to shredding followed by hydrometallurgical processing. The advantage of hydro is the potential for the recovery of more materials, namely lithium, but in the case of pyro, we can benefit from large exothermic potential of battery modules instead of spending huge resources to prevent the fire from taking place. Umicore demonstrated smelting of batteries in isosmelt type of furnace, making copper nickel cobalt alloy followed by hydro separation. In the view of lower overall volume of batteries for recycling in the near future, the integrated process where sulfide ores are treated together with batteries may be more economical compared to dedicated battery-only infrastructure. A step in this direction is a recent patent by Stuart Nicol describing the production of matte instead of alloy. This process has lower temperature compared to the current Umicore's approach. Since this conference takes place in North America, I would like to use some imaginations and dream about the possible future of pyrometallurgical industry in this region. The history of pyrometallurgical processing of sulfide concentrates in Canada is very long and the infrastructure exists, but it is aging. The reserves of concentrates are large, but they are getting higher in MgO, lower in nickel, which makes them hard to be processed in a furnace like Inco flash smelting. Next to Canada, we have USA, which may generate volume of batteries significant enough for recycling to be economical. Of course, the collection and transportation costs are high, but municipalities will likely search for opportunities not to dump them in landfills for environmental reasons. These initiatives are likely to be supported by taxpayers. In places like Australia, the volume is quite small. In Europe, the regulation of battery transport will likely undermine any efforts to create large-scale processing facility. But in North America, a large-scale recycling is feasible. Unprocessed batteries are high in aluminum, contain lots of copper, but also have high calorific potential. Also in USA, there are other types of minerals. In this very conference, there are presentations about pyrite from Iron Creek, Idaho. This cobalt-containing mineral can supply extra sulfur needed to convert battery metals into matte. It is also high in calorific value. Further in the presentation, I will demonstrate that these four different types of materials are quite complementary in terms of fluxing. Let's say the governments of USA and Canada settle their differences and agree that having a large integrated refining hub for nickel and cobalt in North America is quite important for economic and security reasons. Now we can create a place which is large enough to actually compete in operating costs. But the requirements for such operation are high and will need investment in infrastructure and R&D. The composition and proportion of these feed materials may vary in time, so the smelting operation should be flexible. The furnace must be efficient from the kinetic point of view, have a vigorous mixing and supply of oxygen. Molten slag must be in direct contact with large chunk of materials, providing an efficient melting. Slags must be able to transfer oxygen, which can be achieved if it contains iron 2+ and iron 3+ in large concentrations to promote the electron hopping mechanism. The operation must be tolerant to the presence of small proportion of solids in slag. Also, from reading the Valley's report, I can see that the arsenic is a growing problem. Similarly to copper operations, arsenic can evaporate before distributing between slag and matte, but if the mechanical dust carryover is high, the recondensed arsenic will be recycled together with nickel-containing dust back into the furnace, accumulating in the process. The preferred smelting process is the one with low volume of mechanical dust carryover, because small quantity of dust is easier to process via leaching, thus bleeding arsenic from the flow sheet and preventing high partitioning into matte. The main product of smelting will still be slag and matte, similar to the current Inco flash smelter. Thus, the existing infrastructure for matte converting and refining can be used. I would like to demonstrate some calculations using thermodynamic database working with FactSage software. This approach can be used to design and improve various processes, as well as train process engineers using the digital twins. The case study in this slide demonstrates the example of thermodynamic calculations for such a process. Calculations were performed using FactSage plus Excel macro interface and the database for consortium members, with some elements added as dilute components. The main input is a concentrate typical for Canadian smelters. The moisture content is higher compared to flash processing. The second feed is lower grade concentrate, which is also high in MgO. The next feed is unshredded batteries. They contain cathode metal parts but also still have casings, plastic and graphite. In this process, nickel, cobalt and copper are recovered. Everything else burns into gas or goes into slag. We still use silica flags. Then we can feed the pyrite containing nickel and cobalt. It actually plays an important role bringing iron in the system, which I demonstrate in the next slide. And the converter slag from the next step must be recycled back. The blast is moderately enriched air with 46 volume% oxygen. Operating at 1300 degrees Celsius results in 20 megawatt heat loss of in other words, the heat is produced and must be released into the environment. The process does not need fuel for normal operations. Energy balance can be controlled by oxygen enrichment. The furnace produces slag and matte mixed together, so a separate vessel is required for better recovery. The best one is electric furnace. Still, the slag contains suspension of olivine crystals which have lower density and should float on the top, and about 0.5 suspended matte particles, which can be hard to settle. With these assumptions, the recovery into matte is calculated to be 91.5% copper, 95.2% nickel, and 49% for cobalt. The matte contains quite a lot of copper by concentration. Iron in matte will be removed in the converting that can be done in typical Pearce-Smith units. The gas should be cleaned from dust. It will likely need quenching to wash away chlorine and fluorine. Unburned plastics can be an issue, requiring good afterburn on the furnace exit. Here we have simplified slag chemistry of the smelting process. The diagram is at 1300 degrees and relatively reducing conditions corresponding to low grade matte. In nickel smelting, we need to flux iron with silica, but compared to copper smelting, high content of MgO in concentrates requires increased temperature. The region of fully liquid slag is highlighted. It is limited by the formation of spinel from below, the formation of Mg2SiO4 olivine from the left, and tridymite from the top. From the viscosity point of view, it is beneficial to be further away from silica, close to spinel formation, but the formation of suspended crystals of olivine or spinel should be controlled. Small fractions of crystals can be beneficial for high agitated furnaces as described above, because it reduces the refractory dissolution into the slag. Now, if we introduce low-grade concentrate, we will have too much of crystalline olivine in the slag. It is not possible to flux it by silica alone, but there is a pyrite source which together with silica can shift the overall slag chemistry towards lower MgO. Pyrite here acts not only as a source of energy and sulfur, but also as a fluxing for low-grade concentrate. We also have batteries. They don't have much MgO, SiO2 or FeO, but they do have aluminium, which is converted into aluminium oxide. Typically, Al2O3 is considered a problem, hard to flux, but in this case, the solid phase of concern is olivine, and the presence of aluminium 2O3 in the slag increases the solubility of MgO. Batteries provide energy but lack the sulfur to form matte. Thus, pyrite is also complementary for lithium-ion battery recycling. The converter slag comes back and it is already fluxed with low MgO concentration. From the point of view of slag chemistry, we are running experiments and thermodynamic modeling for the solubility of MgO in slags, dissolution of nickel in olivine, effect of alumina 2O3 on the spinel liquidus, and the solubility of nickel in slag. The matte produced during the smelting and settling in electric furnace still contains iron. It is removed through oxidation, typically in Pearce-Smith converter. This is done in two steps, bringing the concentration of iron to 0.6 weight percent. The resulting product, often called Bessemer matte, belongs to the copper-nickel sulfur system with impurities. It is then cooled down very slowly so that precious impurities concentrate in metallic magnetic part. It can be separated after crushing and flotation. Important areas of research here are liquidus of the FCC phase, hazelwoodite and digenite, as well as their mutual solubility. This is the overview of the current thermodynamic database developed with the support of sponsor companies. The elements and phases important for nickel cobalt are highlighted. The phases that were mentioned so far were liquid slag, matte, olivine, spinel, solid metallic FCC, digenite, and hazelwoodite. But there are many more solid compounds and solid solutions and stoichiometric compounds in the database. But to say whether the thermodynamic database is good or not is not enough to see how many elements are included. The accuracy of predictions can be tested and improved by extensive literature analysis as well as targeted experimental studies. Here we demonstrate an agreement between model predictions and multi-component experiments made by Japanese researchers from Tohoku University. These are very challenging experiments to run, and predictions rely on dozens of binary and ternary systems which were modeled before. All diagrams are plotted as a function of weight percent nickel and matte. Oxygen partial pressure increases as expected, and it is higher for high SO2 conditions. The chemical solubility of nickel in slag increases. And the accuracy of model predictions is within 0.2%. Please note the scale. It's quite small. The solubility of sulfur in slag is likely overestimated by the current model. The iron 3 plus versus total iron in slag is significant and reasonably well predicted by the model. Higher values for PSO2 equal 1 atmosphere is likely an experimental issue. The next to the diagrams, we demonstrate the maximum iron concentration and MgO concentration in saturation with olivine. They are reasonably well described. Our model for matte also considers the solubility for oxygen, which is reasonably well described. The concentration of sulfur in matte is an important parameter, but unfortunately was not provided in this experimental study. In the follow-up study, the distribution coefficients for impurities were also measured. They can be modeled. The distribution coefficient is the ratio of concentrations in slag versus matte. They are typically presented in logarithmic scale because they vary so much. Overall, the model is believed to describe the distribution coefficients for copper, cobalt, silver, and bismuth within the accuracy of experiment. For antimony, there is some underestimation, and for arsenic, overestimation. For arsenic, it was recently remodeled to lower values, but the model is still a bit higher. For comparison, the distribution coefficient of arsenic using calcium fluoride slag chemistry is also provided. They might have applications during the converting to control the partitioning of arsenic into matte, but they also dissolve high concentrations of nickel. Previous slides were for nickel-based mattes with low concentrations of copper. The same authors also had a study for high copper mattes with copper to nickel ratio of 1. The model works reasonably well, but the concentrations of nickel in slag seems to be overestimated. We believe there's a fundamental problem in the model for matte starting from the copper-sulfur system, pushing nickel into the slag. But this problem is hard to fix. We already spent significant resources in these directions, but no breakthrough so far. The distribution coefficients for high copper mattes are also described, with some unusual behavior for bismuth. This is something to be addressed either experimentally or using further modeling. In the available literature, there were some gaps. They were measured recently by my co-author Dr. Svetlana Sineva. Namely, for conditions with high PSO2, shown using magenta color, the solubility of sulfur in matte was not previously measured. And now we can compare it with model predictions. Also, the conditions close to equilibrium with the metal, shown with the blue color, were not studied enough. Conditions in equilibrium with metal are close to what we can achieve in electric furnace if mattes are over-oxidized during smelting, but then reduced back. There is a potential for lower nickel in slag. So to summarize some of the current research directions, they are the solubility of nickel in olivine in slag, for which we have a poster at this conference. These were supported by Kalgoorlie nickel smelter until it's shut down. Another research direction is an improvement of copper-nickel-sulfur system and related systems. The miscibility gap between copper 2S based matte and metal is not described very well by the current model and proved to be very challenging to fix. Another recent study is the effect of alumina 203 on the solubility of nickel in slag. The model predicts well up to 4% aluminium, but then underestimates when we move into high alumina, high SiO2 region. Also, an important direction is fundamental studies in arsenic-containing systems. These are not very well investigated in the literature. We achieved significant improvements in the database, but there are some challenges to push accuracy even higher. For instance, in this diagram, if we try to destabilize the liquid, we also compromise the distribution coefficient of arsenic between slag and matte. I would like to thank the long-standing sponsors of our fundamental research. Current activities in nickel cobalt are funded through the consortium of several companies indicated here as copper or nickel, and by our RC linkage program. We are happy to welcome Codelco, Atlantic Copper, SMOS Group, and Valterra Platinum in the new 2025 consortium.